Welcome back to this program, My Teacher, and we are on the way of discussing a few questions in connection with the chapters in physics, grade 12. So, a few questions we already solved. These questions I have taken from the past papers and sample papers. The chapters we focused were from electrostatics to magnetism. Okay, so we are moving on to the next question, but before that, again let me tell you, while you prepare for the examinations, any clarifications if you require, you can definitely get back to us. Okay, so this is again, it's a sort of big classroom now, so feel free to converse. Alright, so now look at the next question. This is a question from chapter electrostatics. Have a look at the question. A dipole is placed in a uniform electric field. Show that the net force, this is one of the sample paper questions, okay. Net force is, net force is 0. We are going to prove that the net force is 0. But is over here, this is, and two questions are there. First question is we have to show that the net force is 0, and second question is the dipole aligned parallel to the field, find the work done in rotating it through an angle of 180 degree. To rotate through an angle of 180 degree. Both the questions we will solve. Now listen to the board. Okay, so this is a uniform electric field and a dipole is placed at an angle theta, let us say. We are going to find out, we have to prove that the net force acting is 0. So this charge is kept over here. The charge experiences a force. What's the equation for force on the charge? F is equal to QE. And on a positive charge, the force will always be along the direction of the electric field. So we can draw a direction of force like this. This is a force, QE. Similarly, on the negative charge, the force owned by the electric field will always be against the direction of electric field. You see, this is the direction of electric field. So QE is one force, QE is another force. Both the forces, they are equal and opposite. Right. So each force is QE. So what will be the net force acting on it? The net force is QE minus QE. So the net force is 0. That's it. That means we proved that the total force acting on the dipole in a uniform electric field is 0. So as long as the field is uniform, the force on the dipole is always 0, because each charge experiences same amount of force, but charges are equal and opposite, no. So the forces will also be equal and opposite, so they will cancel off. So net force is 0. What else we can make out from that? If net force is 0, we can say that there is no translatory motion. It is not moving away from its position. There is no translatory motion because there is no net force. But there is a torque. We have seen the equation for torque. Tau is equal to Pe sin theta. Right. But here the second part of the question says we have to calculate the work done to rotate the dipole. Initially the dipole is along the, aligned parallel to the field. Parallel to the field means theta is equal to 0. Now it is to be rotated through an angle 180 degree. How much is the work required for that? How do you find it out? We know the equation for the work done is Pe into cos theta 1 minus cos theta 2. This is the expression for work done, right? That is Pe into cos, initially it was aligned along the direction of the field, minus cos, and it is rotated through an angle 180 degree. Cos 180 is minus 1, cos 0 is 1, 1 minus minus 1. So 1 plus 1, which is 2. So what's the answer? 2 Pe. So this is the work done to rotate a dipole from 0 degree to 180 degree. Right. So you have to make use of this equation for that. Is the point clear? All right. Now you can look at the next question. You see the next question. Next question also is from electrostatics. First you have a look at the question. A test charge Q is moved without acceleration from A to B. So this also is a sample question. Along the path from A to B and then B to C. So A to B, then B to C. Okay, the coordinates are given 2, 0, then here 6, 0, and for B 2, 3, and it's all placed in a uniform electric field. Charge Q is moved. The strength of the electric field is given as E. Two things you could find out. Calculate the potential difference between A and C. Potential difference between A and C. Now you look at the board. Okay, look here. The potential difference between A and C is the first question. How to find the potential difference? You know, basic equation we can make use of is, in general, potential difference, we have one equation, E dot dl. This is one equation we have seen for potential difference. Or we can even write it as what? E dl cos theta, because dot product. This is the equation we can use for calculating the potential difference between A and C, right? Between A and C. E is E. dl is this distance, you know, this distance is how much? 6 minus 2, 4. Okay, cos from A to C. Cos, how much is the potential difference between A and C? Okay, so the cos, this is where we are going, A to, actually what else we can make out is, it is moved from A to B, then B to C. But it doesn't make out any difference, because you know the potential difference, you know, the work done, potential difference is basically work done. Electrostatic field is what kind of field? It is a conservative field. That is, work done does not depend on the path followed by the charge. Work done is path is not a factor. So that is why we even if it is given as A to B, then B to C, the potential difference to calculate, you just need to consider the points A and C only. The path is insignificant, correct? And cos 0, this angle you can take it as 180 degree, which is minus 1. So the answer is minus 4E. Okay, potential difference between A and C we have. Okay, now one more question is there in that. At which point of the two is the electric potential more and why? That is, C or A, where is the potential high? Which potential is higher? Can you make out? Which potential is higher, A or C? So always you remember the direction of the electric field is from positive to negative. The arrow is like this, that is positive to negative. And potential is always high near the positive side and low near the negative side. And where is the high potential? Therefore, this side. Okay, because the direction is like this. This is negative, this is positive. Near positive, high potential. So out of C and A, where is high potential? C is coming as the high potential. So the answer to that question, where is the potential more? Okay, C. Why? Because it is closer to positive charge. Is that clear? All right. Now you see the next question. The next question I am giving you from chapter magnetism. Look at the question. A galvanometer can be converted into a voltmeter to measure up to V volts by connecting resistance R1 in series with coil, V by 2 volts by connecting resistance R2 in series with its coil. Find R in terms of R1 and R2 required to convert it into a voltmeter that can read up to 2V volts. I hope all of you read the questions carefully. This is again a question from one of the sample papers from the chapter magnetism. Okay. Yes, now I will show you. See, the question is, I will say once again, the galvanometer is to be converted into voltmeter. You know, what is the way to convert a galvanometer into voltmeter? We have studied that. A galvanometer can be converted into a voltmeter by connecting a very high resistance in series. Very high resistance in series. So the equation we have there to calculate the, or to find out how much resistance is to be used, is V by Ig minus G, where G is the galvanometer's resistance and V is the maximum voltage to be measured, and Ig is the current required for producing full deflection in the galvanometer. Okay. So we have this equation. So that's the equation we are going to use. But what is asked here is, what's given in the question is, we convert a galvanometer into voltmeter by connecting resistance R1 so that it can measure up to V volts. So how do you write that? R1 is equal to V by Ig minus G. Let me take this as equation 1. This is the first case given. Okay, now the second case, what is given? V by 2 volts, we are converting it into a voltmeter that can read up to V by 2 volts by connecting a resistance R2 in series to the coil. That means in the place of R1, you can write now R2 is equal to, what's the voltage which can measure up to, is V by 2 by Ig minus G. This is the second equation. Okay. All right, V by 2. Okay, this 2 you can take down also. V by 2 Ig minus G. This is second equation. Is that clear? What exactly we have to prove is we are going to get an equation for R in terms of R1 and R2. I know what is R. It is the resistance required for converting it up to a range of 2V volts. If the question is not clear, once again you look at the question, you see the question once again. A galvanometer can be converted into a voltmeter which can measure up to V volts by connecting a resistance R1 in series with the coil, and V by 2 volts by connecting resistance R2 in series with the coil. Find the resistance R in terms of R1 and R2 required to convert it into a voltmeter that can read up to 2V volts, Alright, now you look at the board. Okay, R in terms of R1 and R2. Now before going to the third part, is third equation also L frame. V R is equal to, what's the maximum voltage we are going to measure? 2V by, instead of V we write 2V by Ig minus G. Third equation. So we made 3 equations. What easy way is, just what you can do is subtract 1 minus 2. So what is equation 1 minus 2? V by Ig minus V by 2 Ig. This is 1 V by Ig, this is half V by Ig. 1 minus half is half. So we get what? V by, that is first left hand side is what? This minus this. R1 minus R2 is equal to what do we get? V by 2 Ig. Minus G minus minus G, that will be cancelled. That's gone. Correct? So we get, what is V by Ig therefore according to this equation? V by Ig is equal to 2 into R1 minus R2. It's clear? V by Ig is equal to 2 into R1 minus R2. Okay. Now again you see the equation. Next what I will show you is equation 3 minus equation 1, you check. This minus this. What will you get? R minus R1 is equal to 2V by Ig minus V by Ig is what? V by Ig. Is it clear? R minus R1 is V by Ig. But now V by Ig, we have an equation we made for V by Ig here. What it is? That is R minus R1 is equal to, okay, 2 into R1 minus R2. This I substituted for V by Ig here, right. Therefore, what is R? R is equal to, I am taking R1 to the other side, removing the bracket 2R1 plus R1. So, that is 3R1 minus 2R2. This is the answer. So, once again I will tell you about the question. There is a galvanometer, we can convert it into a voltmeter by connecting a resistance R1 in series with it, so that the range becomes V. Okay. Another galvanometer, sorry, the same galvanometer to be converted into a voltmeter which can read up to V by 2 volts, we connecting resistance R2. Okay. Then third case, we increase the range up to 2V, for which resistance to be connected in series is R. Okay, so what the question is, express R in terms of R1 and R2. Express R in terms of R1 and R2. Clear? This is what the question, and this is the final answer we are getting. What if you understood? That is, we made 3 equations. First minus second will give you this. Okay. Then again, third minus 1 will give you this. Substituting V by Ig over here and rearranging, we get R is equal to 3R1 minus 2R2. Is that point clear? Okay. Now you see the next question. One second. Yes. See the next question. Next one also I've taken from the chapter magnetism only. Look at the question very carefully now. Okay, I'll just quickly explain because a few more questions we have to do. Okay, I think you got a question. You read the question. This is 4 centimeter radius. Okay. The current is 1 ampere in the first coil. Okay, I'll read the question once again. Two coaxial circular loops L1 and L2 of radii 3 centimeter and 4 centimeter are placed as shown. What should be the magnitude and direction of the current in the loop L2 so that the net magnetic field at the point O be 0? Okay, now you can look at the board. Okay. See, we are going to find out what should be the magnitude and direction of the current here in this coil so that the magnetic field at this point should be 0. See, if you look from this side, always you remember about one general aspect to understand is, if the current is flowing in the clockwise direction, the magnetic field at the center would be into the plane using right hand thumb rule. Current clockwise into the plane, anti-clockwise the magnetic field is outwards. That means if you look at the current over here, from this side you see current is in the anti-clockwise sense. So, the magnetic field is outwards. Okay, so that means like this. Okay. Now, if you face the coil from this side itself towards, that is facing towards right, facing the second coil, how should the direction of the current be then? In order to have a magnetic field in this way. This way means outwards. That means it should be having current in the anti-clockwise direction. You see, you are looking from this side. Looking from which side, that you have to mention. The current is anti-clockwise, so that the magnetic field due to the second coil is this way. This is due to the first coil, this is due to the second coil. So, if you face the second coil, the direction of the current should be anti-clockwise. That is one thing we can make out. And we need to know magnitude and direction of the current. Okay. See, the direction of the current is like this. And what's the magnetic field supposed to be here is 0, no magnetic field. What is supposed to be the situation? These two magnetic fields should be cancelled. B1 should be equal to B2. Then they will cancel off, then the net magnetic field at the point O would be 0. Alright, so B1, how do you write an expression for B1 here? B1 is the magnetic field to first coil. Direction of magnetic field to B1 is, we have seen the equation for magnetic field at a point on the axial line. Mu 0 I R squared is the R1 squared by R1 squared plus X1 squared the whole raised to 3 by 2 should be equal to, this is the first current I1, mu 0 I2 R2 squared by 2 also is there, 2 R2 squared plus X2 squared the whole raised to 3 by 2. So, we equated the two magnetic fields, mu 0's and 2 cancel off. Now, there is an easy way of calculation over here, because look at the data given, R1 squared plus X1 squared, that is here as far as the first coil is concerned, 3 centimeters radius, 3 centimeters radius and 4 centimeters the distance. This is X and this is radius. So, this is what, therefore 3 squared plus 4 squared. How about for the second coil? Radius is 4, distance is 3. So, this is 4 squared plus 3 squared. So, 3 squared plus 4 squared, here 4 squared plus 3 squared. So, what does it say? Therefore, both are same. Both are the same, just you can cancel those two. So, what will be the easy way therefore calculation? I will write it here. I1 R1 squared is equal to I2 R2 squared. What the question is? Question is to find out I2. I2 is equal to I1 R1 squared by R2 squared. Right? I1 is how much? It is given 1 ampere. R1 is 3 squared. So, 3 squared by 4 squared. That is 9 by 16. So, remember the answer is 9 by 16 ampere. If you got it, that is, once again, what was the question? There are two coaxial coils, and we are going to find out the magnetic, we are going to find out the magnitude and direction of the current in the second coil, so that the current is should be in such a way that at this point the net magnetic field should be 0. Zero magnetic field to be there, the field produced by this coil should be cancelled by the field produced by the other coil. This coil produces a magnetic field in this way, the other coil should produce in the magnetic field in the opposite direction, so that the net magnetic field should be 0. Correct? They are equal and opposite. So, I equated both the magnetic fields, and because of these two data match, so we can cancel them off. Then we get the equation for I2. I2 is current into 3 square by 4 square. So, the answer is 9 by 16 ampere in the anti-clockwise sense if you face the coil. Okay, this is the answer. Anyway, I hope you understood the question and answer. Today time for the today's class is going to be over. So, we are to stop it, even if we have a few more questions in store, we will be able to take it out in the next session. But still, if while you prepare, if you have any queries, you can write to us in the mail ID also, you can check. And at the same time, I hope all of you are in the serious preparations for the exams coming in the next week, and some of you have FA2 in the coming week, and even first time examinations in some others. Whatever is the case, prepare it effectively and try to solve as many numerical problems, application level questions as possible from physics, then only you will be able to score good marks in the exams. So, not simply going through the notes alone and learning theory content alone. If you prepare and go, then it will not be sufficient to score in the examinations. So, be very particular in solving as maximum number of questions as possible. Today it's a time for us to wind up. So, stay tuned with NTV, and we will see again in the next week with another topic, other set of questions. Stay tuned. Bye bye.